I am Hagit Grushks-Cohen, and I am from Azure Observability, and I am really excited to be here today. And I'm going to talk to you today about alignment approach for ML project management, or in other words, why we invested in simulation instead of in optimizing the model more. I want to start by apologizing to all these shipping industry people that join us to learn how to optimize containers, different kind of containers. Okay, so I'm going to start by defining the problem, and then I'm going to present our use case and the terminology, and then we're going to do some experiments, and then I'm going to drill down into the simulation. Okay, so just like described before in the previous presentation, a data science project starts with the customer facing a problem, teaming up with the data scientist and many times with the PMs to work to understand the problem better and to rephrase it into ML terminology. So there will be a stage of data exploration and data modeling. And then once we have a model, we will train it and optimize it to provide a solution. And for me as a researcher and also to other data scientists, it's really easy to get carried away with the optimization because, you know, this is where all the juice is at. And we know how it's the more obvious path. We know how to add more features and do the cool stuff that we do. But when doing that, it's really, we must ask ourselves if investing more in improving the model accuracy is the right place to be, because what would improving the model by 5% or 10% or 20%, which is amazing, mean to the end customer? And you know, investing this effort it takes time. So let's say I invest a month of work in improving 5% of the accuracy of my model. Is it worth it? So that depends. The answer is it depends on whether your model is aligned with the business problem or the KPIs or not. That is like, let's say that your model directly, you're building your recommendation system and your model directly affects the click-through rate, then increasing the click-through rate by 5%, it's amazing, right? But mostly, in most of the cases, we're only solving a sub-problem on the way to solve the business problem. And then it's hard to estimate if adding 5% of accuracy to the model is the right investment, or if it is the investment in the right direction. Okay, so now that I've presented the scope in general, I can go into our use case. Okay, so we are talking about increasing container utilization. And at Azure, we monitor our clusters, and we saw that we looked at hundreds of clusters and telemetry, and we learned that the utilization is low. And it is low because it is hard to estimate the resource requirements. And I'm going to convince you why it's hard if you don't really know that already, and talk about how we make sure that our solution aligns with this improvement. Okay, so our goal was to increase the cluster utilization, and not only to increase the cluster utilization, we want to do it while maintaining the service performances. And we did that because we wanted to increase, we believe that increasing the utilization can decrease the lifecycle incidents. And also we wanted, of course, to save money and make the most out of the existing available resources. And the question is how we can increase the cluster utilization safely without degrading the service performances. So I want to start by reassuring you that it works. So we deployed our recommendation algorithm on a large Azure Kubernetes cluster on one of our leading services. It's a huge cluster. And the recommendation recommended on cutting the request by half. And it's, of course, led to saving 50% of the resources, which is big money. And monitoring that cluster before and after the change, we saw that no negative impact on the latencies. And that is despite the fact that during that time, there was a surge in demand of 10 times more requests. So actually cutting the costs and the request supported the surge in demand. So here's a motivation for you why you should optimize your containers. So let's align with the terminology. So when deploying a Kubernetes cluster, we are setting up nodes, which are the machines. And for each node, we are assigning pods, which are services. And the pods are made out of a single or one or more containers. For each container, we have to define the various parameters. And among them, we have to assign the request and the limit. The request is the minimal resource set aside or guaranteed to make sure that the service can perform. And the limit is a value that is the maximal resources that can be consumed by a single container, by a specific container. And that is to avoid resource starvation. And these two values affect directly the scheduling of containers to nodes. So it's really important. So you may come to me and say, oh, well, Hagit, Kubernetes DevOps pros, they know how to maximize the utilization. And I agree. There are these wonderful people that know how to do that, but it's a hard job. They will say that as well. And it gets out of alignment again and again. So building a recommendation system can really help them as well. And most organizations, they don't have that kind of person. So they end up with having a very bad utilization, and that is just wasting money, throwing money down the drain. How bad is it? So this is a graph of one of our clusters, but it's one of many. So 99% of them look like this, and we can see that. Let me show you them. So the lower line is the aggregated consumed amount of cores. So we can say that this specific cluster consumed about 500 nanocores. And the upper line is what they requested, is the aggregation of the requests. So we can see that while using 500 cores, they requested for somewhere in between 2,700 to about 3,000 cores. So we can see that here there is a waste of over 2,000 nanocores, which is 4 times the amount that they use. So there is a lot of room for improvement and a lot of money going down the drain. So let's experiment a little bit and to understand the problem and the motivation and the complexity of the problem. So let's say, for simplicity, that we are deploying a cluster made of a single node, and this node is at the size of 8 cores. And for simplicity as well, we only have one type of container or service that we can have many instances of. And for the sake, and this experiment, we're trying to compare between the different feasible allocations of 3 different recommender systems. Or models. So we have 3 models, one of them recommending requesting 8 cores, the other one recommending requesting 4 cores for this container, and the third one recommends requesting only 2 cores. So for the first settings, we try to schedule containers to the node, and we can see that since the node is requesting 8 cores, and we only have 8 cores available for the node, we can only assign a single container to this node. The second model allows assigning 2 containers to this node, and the third model allows assigning 4 containers to the same node. So we can do 4 times the job in theory. And so you might ask now, well, but how do you know that the node can support that load of 4 containers? And so let's continue our experiment and validate it. So just to understand the calculations, as we said, the allocation or scheduling is affected by the number or the aggregation of the requests. So as long as we still have available capacity for the request of the new node, we can allocate it or assign it to this node. And then the utilization is not affected by the request, but only by the actual usage. So it will be the aggregation of the total usages out of the capacity. And our goal was to increase the utilization. So if we aim to increase the utilization, we necessarily need to increase the usages. But the usages are not something that we control, right? It's the amount of resources that are used by the service. So the only way that we can control it is by, or sub-control it, is by adding more pods to the node. And then you might ask, well, what's going to happen when the workload exceeds capacity? So we must keep in mind that we're still in Kubernetes, and if we exceed capacity, we scale. So back to our experiment. So we are still at the same experimental settings, and now we're trying to schedule 4 containers to our nodes, to our cluster. So we have 4 containers with the following usages. So the first container is using 4.5 cores, and then the second, third, and fourth are using 1 core, half core, and 1 core respectively. So for the first recommender system allowed scheduling only a single node. So our utilization would be 4.5 out of 8. And I'm reminding you that this is a lucky draw, because if the first container that tried to be scheduled is the one of the 1 core, let's say, the utilization would have been even lower, much lower. The second model utilization is 5.5, and the third model utilization is 7 out of 8. So we can see that 7 is below 8, so that all the services will work well. And also, because 4.5, while container A requested only 2 cores, as long as 4.5 is below the limit, then and not all the containers peak at the same time, then the node would be able to provide enough resources for the 4 containers to work together. Okay, excellent. So now we understand the problem and the complexity of the problem. So let's try to return to formulating it as an ML problem. So what does the output to the end user should look like? So our users are deploying these clusters. So they need 2 values, the system to provide them with recommendations for 2 values, request and limit, 1 for CPU and 1 for memory. So in total, we have 4 values. And then what about the solution approach? So we are predicting time series. And as I said before, we are at Azure Monitoring. We collect historical data, so we know the usages of our clusters. And ideally, we would like to predict the future demands of the clusters based on their historical data. To do so, as well as to modeling approaches, we can choose one of many approaches available. We can use this statistical estimators, we can use ARIMA, we can use some sort of Fourier transformation, we can use tree-based LSTM, transformers, etc. And so let's say that we have a model, and I can tell you that in our project, I've built a model, and Jeremy working with me also built a model, and we had a baseline from another solution at Microsoft providing recommendations for these assignments. And also Rachel, our team lead, developed the third model. And now we have all these models, and we need to understand if we want to improve them by, adding more features or improving the accuracy, or even to understand how we are predicting the demand. So how do we translate that into the recommendations? And we want to know which model should be deployed, right? So which outperforms the others. And as I said, our goal was to increase utilization without degrading performance. So we have we need to understand the impact of our predicting demands, how it affects the utilization and performances. So this is where Kubernetes request model playground comes in handy, because normally when we evaluate our models, we use train test approach, and here we're talking about time series. So we would split the data to historical data and test it on the future data. And if we want to be robust, then we would use k-fold, so you can use sliding window. But this setting is not good enough for Kubernetes. And that is because at Kubernetes, we have, even though we can use historical data and perform well on the test set, the data keeps shuffling. The containers move around, the scheduler and the autoscaler shuffle the scheduling, and not necessarily the scheduling that we tested on would be the future scheduling. So, and also, as scheduling event can be brought on by bad luck, so we can have 2 containers with peaking at the same time, allocated at the same node. So we want our model to be agnostic to that, and to provide good recommendations that can support these scenarios as well. So we want to our evaluation to be independent of the specific scenario so that we don't overfit to a specific settings. And it's hard to understand which model is the best one to be deployed safely. Or in other words, we want to plan for as many possible future scenarios. So how do we do that? We were inspired by OpenAI Playground to evaluate reinforcement models. I don't know how many of you are familiar with these two little blue guys pushing around these yellow boxes, but this project was done a year ago. At that time, ChatGPT was not this widely associated with OpenAI, and OpenAI was associated with the Playground. And just like the Playground, we wanted to test our models on realistic settings and, after our requests are already set. And we wanted to use the real data that we have because we have tons of real data. And so our solution was to use the real data that we have to produce more data. And working on this tech, I realized that the way that we trained our model and worked with our simulation has some similarities with RLHF, but in this case, it's more simplified, so we don't really need the human feedback stage. So how does simulation work, or how did we apply simulation in this case? So the simulation is, to simplify the simulation, we simulate a future scenario of a scaling of a new node. So we're assuming that we have already a cluster working, and now we have an event of scaling, so we have a new node that we need to schedule containers to. And if we want to make the experiment more robust, we can start the simulation with sampling services. But let's say we are looking at the simplest form of simulation. So we're already trying to optimize or find the optimal model for a specific service. So we're starting with we're basing on the historical data of a specific service. And with this settings, we are choosing our experiment setting. So this experiment, a single experiment in this setting would be scheduling containers to a single node during a specific time. So to define the distribution of usages, we randomly sample a time frame from the historical data of our service. And this time frame produces two factors. So the first one, it tells us which containers were available or active during that time frame. So looking at the historical data, we learned that not all containers are active all the time. And the second thing it provides us is the distribution of usages, as I said. So we would use the usages from this time frame as a basic for the sampling. And we also choose a node from the node pool or sample a node from the node pool, and this defines the available capacity of our cluster. Or the node that we're trying to schedule to. And we're doing a stress test. So we're scheduling the containers keep coming until we can't schedule any more containers to the node. So the experiment goes repeatedly. We're repetitively trying to schedule a new container to the node, and we can schedule as long as the requested amount is below the residual of the capacity. So we draw the requested amount from the model that we're trying to compare, and the usage is drawn from the actual usage as witnessed during this time frame for the specific selected container. And we would add more and more containers and aggregate their request to know if we still have enough capacity to schedule another container, and to the actual usages to understand the utilization of the container. To make sure that we can compare different models, we want to sample fairly. So to sample fairly, we do the following allocation. So let's say that for our experiment, model A, which recommended using 8 cores, which is less efficient than model C, recommendations allowing to schedule 4 nodes, would be a subset of the model B, which is a little bit more efficient, and of model C. So in that way, each allocation is a subset of a more efficient scheduling. And this allows us to compare the different models and make sure that they are comparable. So how do we compare these models? So I was describing a single experiment, and we can perform hundreds or thousands or hundreds of thousands of experiments to validate the robustness of our solution. And each experiment would necessarily change the settings, so we know that we're not overfitting for a specific setting or a specific lottery. And so for each setting, so for each experiment, we can calculate the utilization of the node by the aggregation of the witnessed usages out of the capacity. And we can also notice or note if we notice a situation of overutilizing, which would mean that we would face the scheduling event, auto-scaling event, sorry. And then we can aggregate them for the entire experiment of many experiments, and we can calculate the mean or median utilization and the proportion of these scaling events out of the total amount of experiments. This allows us to compare the different models. As we can see, each and different dot is a different model results. And which outperforms is depending on the user preferences. So some services would be willing to sacrifice a little bit of their worthiness in order to save more money, and they would prefer the orange model. And then others would say that they want to minimize the events of scaling and even on the cost of savings, and would prefer this model. And so we can incorporate these preferences in our recommendations. Looking at the results of our experiment, we learned that there is no single model that outperforms for all the services. So the recommendations should be personalized for each service, and different services would get different recommendations or different model recommenders. So in this case, for sure, if we would have optimized the single model, we would have missed, we wouldn't be on the spot, right? It would be a bad investment. So if I want to conclude, and what I want you to take away from this talk is that don't get sucked into optimizing the model unless your model is aligned with the business KPIs directly. And then the alignment of the ML project to the KPI is crucial to the success of the project. And also keep in mind that when you're collecting your data or creating your data, it might be biased on the way that you collected the data, biased to the existing algorithms or to luck. So ask yourself, is your data that you collected impacted by something? And in these cases, simulations can help you to overcome that and to do a robust evaluation. And it's also a good place for alignment and to bake the user preferences into the evaluation. So thank you very much for listening. I hope you enjoyed it. And I am up to answering questions or comments on the chat. And you can also, I started a thread on Twitter, so if you prefer, you can also comment there and I'll be available there as well.